Hey there. In Module 19, we are talking about population growth models. And so we use population growth models to predict about the future of our populations, what will it look like in the near future and in long term. And that truly lines up very closely with the goal of science, which is that we try to observe how things work in the natural world so that we can make predictions about the future. And so we have used population models in environmental science to restore condor populations, which we've talked about in the past few modules, and to govern the commercially harvested fish to make sure that we don't overfish, and so that we can still have enough fish to feed a population. And we also use it to control pests and insect populations. So should we spray? If we spray, how much is too much and what will be enough? So these population growth models are very important to answer questions that we need answered. And population growth models can be used to predict a population size at any time. And one of the models that we use is the logistic growth model. And so here we can see that we talked about this over here earlier with the paramecium, how when the population had everything that it needed, when it had all of the food that it would ever want, it wasn't limited by any limiting factors, the population grew very quickly. And we call this J-curve growth. This J-curve growth means that everything is going well and there are no limiting factors. But eventually, there will become a limiting factor. Eventually, once the population becomes dense enough, there will be disease will run through the population because people or organisms live too closely together or will run out of food. And so those are density dependent population factors. And so oftentimes the population will overshoot, so you'll have more and more and more organisms and then run out of food, and then the population will collapse and you reach this homeostasis. This homeostasis fluctuates around the carrying capacity, which is denoted with the letter K. The biotic potential is measured here. This is the amount of growth that is allowed by the ecosystem. So that is the potential amount of growth in the model determined by the resources in the ecosystem. And so we calculate the population growth by subtracting the death rate from the birth rate. So very simply, right here, the birth rate from the death rate, or the death rate from the birth rate. And so every population, depending on ecosystem resources, has an intrinsic growth rate, and we denote that with the letter R. And that is right here, the maximum growth rate. This is under ideal conditions, represented by this J-curve, also known as the biotic potential. And so there are different things or different factors that allow a population to grow quickly or not quickly. And one of these factors is fecundity, and that is how many offspring a female can produce. And so if you have domestic hogs, they can have 10 piglets at a time. But a bullfrog can lay 20,000 eggs, and so they have greater fecundity, and therefore their populations are going to grow much more quickly. And when the conditions are ideal, the frogs are going to be able to produce more offspring, and more offspring are going to survive because there's more food and space is plentiful. But when conditions are not ideal, you're going to see that overshoot or that crash, and that's because there's going to be not ideal conditions, and so the eggs, if they are produced, may not hatch, and if they do hatch, they may not survive for very long. There will be weak, so maybe they're going to be eaten more quickly, and so they're not going to survive as long. They're going to be in this zone of physiological stress, perhaps, and so that's when you're going to see those overshoots. And so the intrinsic growth rate, denoted by the small r, is used in equations right up here. This is the exponential growth rate model. And the n naught, or n0, or n original, is the number of reproducing individuals. And we can estimate the future population which is N1 or N total. Either one is correct. And so E is the natural log, the base of the natural log equal to 2.72. And T is going to be time. So under ideal conditions, the future size of the population depends on the current size of the population and the intrinsic growth rate and the amount of time it has to grow. So this is going to be the total population. This is the number of reproducing individuals. This is the rate up here, so the base of the natural log, and the rate and time. So if we consider a population of rabbits that have an initial population size of 10, so that's our N naught, or our N original, 10, our number of reproducing individuals. Let's assume that the intrinsic rate of growth for rabbits is R, 0.5, or 50%, which means that each rabbit produces a net increase of 0.5 rabbits per year. With this information, we can predict the size of the rabbit population in 2 years from now. So if we do this math, here we have our initial model, and we said that there are 10 reproducing individuals. E is the base of the natural log. 0.5 is our growth rate, and 2 is the number of years that we are measuring for. And if we plug that into our calculator, we can see that the total rabbits are going to be 27 in 2 years. So we could use the same calculation to predict in 10 years, except so instead of putting a 2, we would put a 10. And so it would look like this. So here we have 10 reproducing individuals, the base of the natural log, 50% times 10, and that gives us, well, that's a lot of rabbits, 1,489 rabbits. So this is called logistic growth. We looked here, this was our J-curve growth, and our logistic curve is taking into consideration the carrying capacity. So we use that last exponential growth rate model to calculate this J curve. However, we know that the J curve can't last forever because resources are eventually depleted. And this is the carrying capacity. The carrying capacity is determined by the amount of resources available, or the lack of resources available. And so different environments are going to have different carrying capacities. And sometimes even the same environments are going to have different carrying capacities at different times in the year. If you remember the Texas mosquito mystery, the same environments had different carrying capacities in different years because of the amount of rain. And so we use this model here. It is used to predict populations using density-dependent variables. So eventually the population becomes too great, and it affects the survivability of offspring. And so density-independent variables are too random and not predictable. And so we can't use these to determine our logistic growth. Carrying capacity is calculated for current time, however. Some mammals mate, and in the fall and winter, when the seasons are plentiful and there's plenty of resources. However, sometimes the next season may not be as good. And so that's where we get our overshoot. Right here, we were talking about that overshoot. So everything's good, everything's good, everything's good, and all of a sudden resources run out when the offspring are born in the spring, and that's when we have our crash here. So this is our overshoot, and it results in a die-off right here. And so there was a famous historical die-off in the 1940s in Alaska and on St. Paul Island, where there was lots and lots of reindeer, and then all of a sudden they reached their carrying capacity. All of the lichens were eaten, and that's what reindeer eat, are lichens, and so all of a sudden the population crashed in a pretty tragic way. Predator-prey relationships are another example of density-dependent population factors. We have the famous example of the lynx and the hare. So as one population goes up, the other one goes down, and one goes down, the other one goes up. This information was collected, interestingly enough, from the trapping records of the Hudson Bay Company for 90 years in Canada. They are a company that did the trapping of many different animals. So that's interesting. Another famous example is the wolf and the moose population in the Isle of Royale in Michigan. And so there are a few different strategies, reproductive strategies for organisms. And so let's first talk about the K-reproductive or the K-selected species. So here we're going to follow this blue line. So K-selected species, they have characteristics where they're going to have a low intrinsic growth rate. So you can see how their growth rate, the population growth rate, is much smaller or much slower than the other R-selected species. And so these tend to be your larger animals. They have lower fecundity, meaning they produce fewer offspring, and they take more time to care for their offspring. So these are like your elephants. They don't become reproductively mature until 13 years old and can only breed every 2 to 4 years and only have one calf at a time. But you can see that there's less noise or less fluctuations in this curve. There's less up and down, so the population tends to be a bit more stable. However, it is difficult to restore the K-selected species if they become endangered because they aren't producing as many offspring. If you have an R-selected species, though, it is easier to help an endangered R-selected species because they have a much higher reproduction rate. And so here you can see the population growth rate increases very, very quickly. But there's also lots of fluctuations, and these fluctuations often occur because of density-independent factors. So if we go to our mosquitoes or insects, oftentimes mice, these are going to be smaller organisms. They have lots of offspring. Oftentimes they do not take care of their offspring. So if you have fish in the ocean, they're going to lay thousands of eggs, but they're not going to care for their eggs. And so fewer are going to survive, so it makes sense to produce as many eggs as possible. And so here, this graph is going to be affected by the density-independent factors. So once again, if we look at the mosquitoes of the Texas mosquito mystery, the population died off very quickly when there was lots of rain. And so the population of mosquitoes was once high, and it died off and went down. But then it was another warm year, and so the population went back up. And so these populations are going to be affected by density-independent factors. And so K and R reproductive strategies are two opposite ends of the spectrum, but nothing in life is so simple or dichotomous, so most species fall somewhere in between. If we look at examples of tuna, which are large ocean fish, and redwood trees, these are large species, and they live a long time, but they disperse millions of eggs or seeds, and they don't take time to care for them. And so to help us understand reproductive strategies, we're going to also discuss survivorship curves.